Hi, I'm David. This is a quick little video to show how the present value of a series of regular payments is derived. And there's three different ways I could go about deriving it, and I'm going to show you all three. First, let me give you the situation. This is time, and this is now, and a year from now you'll have a payment, maybe a month from now, or it doesn't really matter what the time period is, and I'm going to call that payment A. And then 2 months from now there'll be another payment, 3 months from now there'll be another payment, and then there'll be a whole lot of them, and then at some point in the future they'll stop. And the number of payments total is N. We want to figure out the present value of these payments. Now, when you do present value, you're trying to figure out what you would have to invest now in order to get the same amount of money in an equivalent sense in the future, which means that you're investing using compound interest. So you need an interest rate to do it. So I'm just going to add that to this. The interest rate equals I. So the concept is, if you had a certain amount and you invested it for a year at interest rate I, at the end you'd have I% extra on top of what you had, so 109%, which is 1 plus I, because I is written as a decimal. So if it was 5%, you'd have 0.05, and 105% would be 1.05, which is 1 plus 0.05. And that's what we do if we were going into the future and waiting for something to happen. But what we're doing is we're looking to the future and we're working backwards to what's going on now. So instead of multiplying by 1 plus I, I'm going to have to divide by 1 plus I. And things that have been compounded in the future would have been multiplied by 1 plus I multiple times, once for each year. So we're going to have to divide by those multiple times to get them back to what it would be now. So the formula for present value comes out to be, my present value is my amount divided by 1 plus I, because my first amount was 1 year into the future, so I've divided by 1 plus I once. And my second amount is 2 years into the future, so I've divided by 1 plus I twice, and then blah blah blah. Eventually I'll get to the last one, which is n years in the future, so I'll divide by 1 plus I n times. And this is a formula. If all of these A's were different, so there was an A1, A2, A3, A4, and they're all different numbers, I would have no choice but to just figure this out as it stands, sub in all the numbers, calculate all the bits and add them up, and that would be my answer. But since they're all the same number, I can use some nice maths tricks to figure out a simpler formula for it. And that's what I'm going to do now. The trick is that we're going to notice that this bit here is very similar to the whole thing, except that instead of starting at 1 plus I, it starts at 1 plus I squared, so all the powers are 1 higher. If we times everything by 1 plus I, then the 1 plus i's on the top would cancel out with one of the 1 plus i's on the bottom, and all of the powers will go down by 1, and it'll look even more similar. So let's do that. So 1 plus I times P is A over 1 plus I times 1 plus I, which is just A over 1 plus I squared times 1 plus I, which will be just A over 1 plus I. A over 1 plus I cubed times 1 plus I will be A over 1 plus I squared, and so on, all the way up to this. The power will be 1 lower because 1 plus I times by cancels out with one of the ones on the bottom. And now, this bit is the same as this bit. It just doesn't go all the way to that last one. So what we're going to have to do is go, well, the bit that I've got here in orange is the same as P minus this. So 1 plus I times P is A plus P minus A on 1 plus I to the n. Now I've got a p on both sides of the equation, but if I expand this side out, it's actually going to cancel out. So p plus ip is a plus p minus a over 1 plus I to the n, and the p's cancel. So I get ip is a minus a over 1 plus I to the n. So we're nearly there. This formula would look a little better if the a's were together, so I've factorized it out. And so I'm going to do that, but I have two options about the way I'm going to do that. One would be to write it over a common denominator, and the other one would be to rewrite that power as a negative power, and I'll show you both of them. I'll just copy out my last line. There it is. Okay, so I could do this. Like that. A power on the bottom is the same as a negative power on the top. And they've both got an a in them, so I can pull the a out. Like that. A times 1 minus 1 plus I to the minus n. And now if I divide both sides by I will get p equals a 1 minus 1 plus I to the minus n over I. And that's one formula. An alternative formula would be if I started with the same thing, IP equals a minus a over 1 plus I to the n, and put it over a common denominator first. So I can times this one on the top and the bottom by 1 plus I to the n, so that the bottoms are the same. And then I get a 1 plus I to the n minus a over 1 plus I to the n. And then I can pull the a out of the top. And then I've still got IP equals this, so I can divide both sides by I. 1 plus I, the n minus 1 over I, 1 plus I to the n. Okay, so that's another formula. You could also have gotten from one formula to the other by dividing. So from this formula to the other one, I could divide everything on the top and the bottom of the fractions by 1 plus I to the n, and it would give me the same answer as the other one. There is one other way to get here. The formulas will come out roughly the same, but I want to show you one more way that we could have done to get here, and that's to use the sum of a geometric series. But I'm going to have to do a little bit more work to make that work. So just note, a geometric series is what happens when you start with a 1 and keep multiplying by the same thing over and over. And so it would tend to look like this: 1 plus q squared plus q cubed plus blah 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 plus, and it will stop at some point. Okay, that's a geometric series. And by using pretty much the same reasoning that I used up there, where I noticed that parts of this looked very similar to other parts, I can prove that this happens to come out to be equal to this. Like that. It uses the same sort of algebra that I used above, by calling this S equals this sum and rearranging it until I can find out what I need, by noticing that it's very similar to what I had before. If I can rewrite the series that I had above like this, then I can use geometric series ideas to prove that I get the answer that I do. So let's see. We have that P is A over 1 plus I plus 1 plus I squared plus A over 1 plus I to the n, which is very close to being a geometric series. Firstly, if I rewrite all of these with negative powers, plus A 1 plus I to the negative 2 plus A 1 plus I to the negative n, then I can notice that if I happened to choose my q to be 1 plus I to the power of negative 1, then this would be like a geometric series. A 1 plus I to the negative 1 squared plus A 1 plus I to the negative 1 to the n, which is AQ plus AQ squared plus AQ to the n for q equals 1 plus I to the minus 1. Okay, so it doesn't look quite like what we need. They've all got an A, so I'll bring that out. Equals A q plus q squared plus q to the n. But it's still not what I want, because to use that geometric series formula I have to start with a 1. So, they've all got a q. I could bring the q out. Plus q to the n minus 1. Excellent. So now this I can use. The geometric series formula up above says that I have to add 1 to that power and do 1 minus that on the top. And just have 1 minus q on the bottom. Cool. So that's a formula for this. I could do this by figuring out what 1 plus I minus 1 is and subbing that in for q. But let's just sub in for q and see what we get. Q is actually 1 plus I to the minus 1. We have 1 minus 1 plus I to the minus 1 to the n. And we have 1 minus 1 plus I to the minus 1. Okay, well, I do have on the top a 1 plus I to the minus 1, and I have on the bottom a 1 plus I to the minus 1. If I multiply everything by 1 plus I, that will cancel out. 1 plus I to the minus 1 times 1 plus I is just 1, and so they'll cancel out. So I could go, this is the same as A times 1 minus 1 plus I to the minus n over 1 plus I minus 1. And so we've got that P equals A 1 minus 1 plus I to the minus n over 1 plus I minus 1, which is the same as A times 1 minus 1 plus I to the minus n over I, because 1 plus I minus 1 is I, which is the same formula that we got before. We just did it using geometric series. Important thing to realize with this geometric series formula is it only works if it starts at 1. And ours didn't start at 1, it started at A times Q. So you need to be really careful when you want to derive it this way, that you have to adjust it in the middle here to make sure that it does start at 1. Okay, so there's 3 ways to derive the 2 possible formulas for present value of a sum of a series of equal payments. One of them is this, and the other one, which uses slightly less brackets, is this one.